In this example, we're going to put together equations for a certain spring and then write them as a system. So our spring is attached in two places, one of them on the left and the other on the right, and there are two masses, and this spring constant is K, and this spring constant in the middle is 2K, and the one on the right is K as well. And so let's call x1 the rest position for this mass that is labeled F, and x2 equal to 0 being the rest position for this mass that's equal to G. And A is the distance from the left wall to the rest position of the first mass. C is the distance from the right wall to the rest position of the second mass. And B is the distance between these two rest positions. So they're constants, A, B, and C. As the masses move, x1 and x2 are going to be the displacements of the first mass and of the second mass from their rest positions, and both masses have the same mass, which we're going to call m. Let's think about the way in which the forces will act. So if x1 is bigger than 0, that means we're stretching the first distance, which means that A is increased, and so the force will be back to the left from this spring K. If the distance between x2 and x1 is bigger than 0, that means that B is increased. So B is stretched. The spring will want to come back, so the spring will pull F to the right and G to the left. And finally, if x2 is bigger than 0, then that means that C is compressed, which means that the force on the mass that we're calling G will be to the left. So let's put all those forces together. The forces on the object we called F are minus kx1 from the left, and then plus 2k x2 minus x1 from the right. The forces on the object G are minus 2k x2 minus x1 from its left, and minus kx2 from its right. And so the forces are the mass times the acceleration. And so we have minus kx1 plus 2k x2 minus 2k x1, altogether minus 3k x1 and plus 2k x2. For G, the mass times the acceleration is minus 3k x2 and plus 2k x1. And so those are our differential equations. We're going to want to write them as a system and then make some observations about that system. To convert this equations that we had for the springs into a system of first order equations, we set x3 equal to x1 prime, so that the second derivative of x1 will be the first derivative of x3. We set x4 equal to x2 prime, and then the first derivative of x3 is the second derivative of x1. And having divided by m, we have minus 3k over mx1 plus 2k over mx2. And for x4, its derivative is the second derivative of x2, and so again, having divided by m, we have 2k over m times x1 minus 3k over m times x2. There are four variables here, so this is a four-dimensional system. It's a first order four-dimensional system. And this system is linear because all the variables appear linearly in the sense that everything on the right hand side, x1 prime is just x3, the first power of x3, x2 prime involves only the first power of x4, and the same is true for x3 prime and x4 prime. They're linear in x1 and x2. So this is a linear system.